Oh, you can hear me, right? Okay, fantastic. Thank you, Taha. Yeah, I hear you very well. How are you? All good? Just so. Hello everyone. The workshop, I think we should start probably after 5 minutes. So basically, just if you are not hearing me or there's any issues, okay. Yeah, the workshop will take 60 minutes. Okay, welcome. So basically, so I think you are all hearing well. We will start soon, just waiting all your colleagues. Okay, hello everyone. I hope that if there's any issues with the sound, please let me know. We'll start soon. Okay. Okay, hello everyone. Just first of all, I would like to introduce myself to you. My name is Mohammed Fouad. I am architect and computational designer. I did my master's degree at IARC in Barcelona. Especially, basically, I am a specialist with additive manufacturing, earth-based composites, and other sustainable materials. Also, I'm with the robot fabrication and digital fabrication processes. So for the moment, I'm doing my PhD thesis at the University of Minho in Portugal and Advanced Ceramic Lab. So basically now I'll just start with you like, so basically the main reason of this workshop, I would like to share with you my back experience with sustainable materials, with robotic fabrication, and also I'll talk about extruding systems and how we can also develop design methodologies for 3D printing complex geometries, for example, as shell systems. So now I'll just start the presentation, and please, if you have any question, like you can ask me anything. So it's like this workshop is more about doing like interaction between each other. So I'll just start right now. Okay, so basically I'll start right now. Like basically my thesis topic is about additive manufacturing with earth and architecture. We're trying to develop computational methodologies for defining shell envelope system. This research, basically, I should say, like, is funded by Foundation of Science and Technology here in Portugal, and also with the University of Minho. So this is like the main topic that I'm developing right now in my PhD thesis. Also, I'll talk with you about like all projects that I did in my master degree, and I'm trying also to develop here in my thesis topic. So the main topics in the workshops, as I shared with you in the email, like basically I'll talk about additive manufacturing with earth-based composites. My previous projects, basically I worked with cantilevers and earth architecture, and we were trying, I'm sorry, just before there's people trying to, okay. People join. So basically I was trying to explain to you later, like we were trying to develop cantilevers in earth architecture, and trying to develop wooden support systems to support the printing process, and also to prevent the buckling issues. And the second project, we were trying to do infrastructures for 3D printing in architecture. So we were developing like a module system, and trying to develop this module in order to be integrated with the neighbors by using construction 3D printing process. And for the moment, also we were trying. Sorry, just 1 second. A lot of people. There's an issue. And for the moment, what we are trying to do, that we are trying to develop self-supported geometries. Okay, in order to print shell structures. And also we are trying to make deep studies by studying the masonry ancient building history, like trying to mimic the building methodologies with Adobe and trying to translate it into the 3D printing technology. I'm sorry, can you please? Okay, I'll just start like now. This is the first project that I did at IARC, my master thesis, and also in OTF, Open Thesis Research Fabrication process. Basically, we are studying in deep like earth material and how to integrate it with the 3D printing process. And basically, we're concentrating on printing only cantilevers, or we can say the corpels. And first of all, we started with the small prototypes. We started to print something without any support and trying to see what actually we're facing basically with the 3D printing process, for example, at like buckling, the buckling issue, since we're trying to print layers of clay. And after that, we start to add some printable supports and to see if that will be helpful to prevent this problem or not. So basically, we tried different methodologies, and also we tried to make like small prototype for temporary support systems, and trying to find out if that will be efficient through the printing process in order to print a complete cantilever, or you can say complete arch, catenary arch. So after these types of experimenting processes, so then we did a transition to a larger scale and trying to print like on wooden support systems with the robots, and trying to find out what is the best way in order to prevent many issues we face through the printing process. Like basically the main issue is the buckling. Also after drying time, we are facing like a shrinkage issue, and especially, as you know, like earth material, it's really work with the compression processes, but with the tension, it's not really work properly. So, okay. After, just I would like to share with you, I'm talking about this project because I want to say like it wasn't really 100% efficient, because mainly we found out like after adding a large amount of wood and trying to print on top of it, and in order to prevent one problem of the 3D printing process and trying to manage it on the construction side. So basically, from my point of view, I was trying now, like in my PhD thesis, to actually to develop more the geometry, and by using computational tools in order to print something already stable, and it doesn't need a lot of support, another material, you know, to support. So that is like now like you can say my tackle, or you can say my goal that I'm trying now to reach in my PhD thesis. So basically in the PhD, you need to concentrate a lot on one point and try to tackle it in terms of materiality, in terms how you can develop the machinery part in order to help you and support you to achieve your goal with 3D printing. So basically, you can say like I'll talk first of all like about the materiality part and what are the issues that we were facing, especially with the earth-based composites. The main issue with the 3D printing process that you need, we found out that we need to develop something after drying time should be less shrinkage issues, you know. So for that reason, we tested two types of earth, one of them from Spain, named by like eco clay earth, and also from Portugal. Here there is a city named by Barcelos. It's really famous with stoneware clay, and the one from Spain is earthenware. So basically, we did different experiments with the different types of fibers, because we found out many researchers, they were trying to add a fiber as a kind of, you can say, to reduce the amount of the water inside the composite, in order to prevent the cracking and shrinkage issue after drying time. But since we were trying and we were trying to add a lot of fibers, we were facing that we need another binder that will help us to increase the plasticity of the material in order to be printable in the construction side. Also we were trying different types of adding different types of aggregates, like fine sand, hard, you can say it was the best one because it was trying also to make, you can say, the ball of the earth or clay more plastic and trying to reduce the sticky behavior of the material. So the main issue, in order to print a clay composite, you need to control the amount of the water. So basically, in order to control the amount of water, we found out after different tests that the more you add water, you're more facing cracking issue with this material. So the more you reduce the amount of the water and adding more binder like sodium silicate and hexatomate phosphate, because it has more, you can say, if we go inside deeply inside the mineralogy of the earth, we need more, you can say, positive ions in order to increase the bonding between the layers. So basically, the more we add water, we'll face most issue with the cracking and the cracking issues and also the shrinkage. So, but once we reduce the amount of the water and adding more sodium silicate with the earthenware type of clay, it was more successful with us through the printing layers of the composite. So after that, after these types of testing with the ingredients of the composite that we're developing through this research, so basically we started to know how we can control and know how much the fiber is absorbing water through each composite. Because once we can develop a formula that will I'm sorry, yeah. So, since we are trying to control the amount of the water and the amount that is absorbed from the fiber that we're adding to the composite. So we did kind of simple experiments, like by developing a mold in order to add each kind of composite, and after that to measure the weight after drying time and before drying, and trying to see the difference between the two phases in order to reach a percentage and know that, for example, this type of fiber is yes, I'm sorry. Sorry for interruption. Like so that was like a methodology that we were trying to develop a kind of formula that will help us to know, for example, this composite would be good for the 3D printings because, like, for example, the amount of the cracking was less. For example, as you can see here, we have two types, like the porcelain and the earthenware that eco clay. So after doing different specimens, we found out a specific composite that we used after this. Okay, sorry, just the slide is not. So actually, as you can see here, we were testing like with the Lutum 3D printing machine, and basically we found out that with the stoneware, basically, with the simple amount of fiber, it was kind of easier to extrude with the earthenware, like earthenware type, like the clay type that I was explaining before. So basically, we were trying to find a formula that control these types of ingredients, like amount of fibers, the binders, the aggregates that we add, and also the amount of water, in order to know, for example, that this composite will be extrudable, first of all, with this type of machine. But in order to reach something, you can say, in order to print, you can say, more complex geometries, basically you need to control different parameters in the machinery in terms of flow of the material, in terms of the extrudability and buildability of the material, and the bonding between the layers. So all these issue is not also just related on the type of the composite that you are developing. It's also related about the extruding system that we are developing. So for that reason, sorry, just open the other slide. Okay. For that reason, we start also in this research to go far with the extruding system, how we can develop something that could extrude these types of composites with the fibers. And actually, it was really a bit hectic, because in order to extrude these kinds of composite, you need to control different parameters and timbers. The torque of the motor, and also the way that you push the material inside the extruder. So for the moment, we are developing also a more advanced system that using more advanced from the pneumatic system. It's more linear actuator pushing system. So in order to extrude a composite with fiber, is really hard to do, but if you can develop something with high torque in order to push this composite, actually you can do it. But for the moment, in my thesis, I'm still developing this system in the coming months, and I will share with you probably like on the website in the university platform, University of Minot. So basically, I'm saying this because basically in the construction side, there's a lot of systems that were developed by, you can say, expert companies like WASP in Italy, and also other companies in different parts from Europe and also outside of Europe. But basically, when you want to go on the construction side, you need to think that how you can add less amount of material, because most of the project that is developed with this material, they add a lot of material in order to be stable through the printing process. And also I'll talk about the infill design and how you can develop something with less amount of material, and also in order to reach in order to reach complex geometries like a vault and dome in easy ways. So basically, in the construction side, they cannot actually, for the moment, especially if you know about the crane system, it's not easy actually to control through the printing process if you want to print a complete shell. If you want to print a vertical wall, it's fine for the moment. So basically now we were still developing this system, the pneumatic system, in order to be successful to print earth-based composites. But the main issue, I'm sorry, just takes time to move to the other slide. But just give me a second, please. Okay. So before starting, like with this topic, like I was saying, like normally in order to extrude this type of materials, you need to control the materiality and machinery part. You need to know that the machinery that you are using, especially in the construction side, that will help you and will support you to extrude these types of composites, and also to support you in order to blend like, you know, advanced geometries like a shell system, you know, with more cantilever, like with different types of cantilevers, because mainly the issue with the cantilever, and especially with the printing process, is really tricky. After doing different experiments on the small scale, imagine like in the larger scale. So for that reason, we were okay. We should back to the masters, the old masters, and trying to study the methodologies that they were trying, studying, building vaults like Nubian vaults, like Catalan vaults, like the Gothic vaults. There's like many types, and many types of many types of ways of building with Adobe, Adobe Breaks especially. So the main idea, we were studying the history of building with Adobe, because you can say it's ancient traditional 3D printing process. So we were thinking, if we study all these types of methodologies of assembling the blocks and trying to translate it into contour layers, because as you know, mostly the most famous methodology with additive manufacturing is the contour crafting. So basically, the contour crafting is like a sectioning method of the geometry that you want to print or you build, and trying to control the contour path. So these issues is really similar. It's really similar of ways of building with Adobe blocks. So we were studying like different types of methodologies, and especially, and we found out that okay, mainly they were trying adding ribs within the geometry to translate, you can say, the forces within the shell system to many parts in order to support each other. So now for the moment, I would like to show you this video. You can see the process of, you know, process of assembling and building the layers in order to be self-supported. So this is the methodology we were trying, you know, to tackle and see in the reality how that will affect through the printing process, small scale prototype for the moment. So as you can see here, we were trying to use a methodology like appentative elements, as it in, you can say, in Hagia Sophia. So they were adding pentatives into Hagia Sophia in Turkey. They were adding pentatives to support, you can say, the dome. Okay. So you have like two types of geometries. You have two types of geometries that you are supporting each other to prevent the buckling issue. So basically, these methodologies we extracted, as I said, we extracted from, as you can see here, like it was a building technique in Hagia Sophia in Turkey, and they were using this element, like pentative element, as a geometry in order to support the whole building. the whole part of the building, you know, the dome or the shell. So okay, and so we found out, okay, we could use this methodology in the printing process. So we found out, like, okay, this is a methodology, and there was also another methodology. We, after studying the topology of the surface, you can say, of the shell. So basically, they were dividing and segmenting a surface to two layers of ribs. So these layers of ribs was supporting the whole surface, or you can say the whole surface or mass of the shell. So you can see here also we tried to do like, you know, trying to translate this methodology into contour layers in the printing process. And actually, for the small scale, it was kind of successful. But in the large scale, we need to study more in deep the material composite that we are doing right now, and that we are developing to fabricate with the robot. So, okay. So basically, as I said before, we are trying to do a comparison between the 3D printing layers, contour layers, and also you can say the Adobe or the monster blocks, and trying to find out what is the best methodology to prevent problems like buckling issues, and also how we can print something stable. So we found out after testing two methodologies, since we are trying to increase the local inertia or the global inertia of the geometry by segmenting the surface of the geometry and trying to add more masses that is controlled in such a way to support the whole geometry in order to reach something self-supported without adding any support or any other material to support. So we started to develop kind of a design table, you can say, and we started from a simple surface of a dome, and we were trying to do different iterations in order to add like ribs, or we can say specific masses within the surface, as you can see here in the profile section. So in order to increase the inertia resistance of the geometry, and also to increase the surface area, you can say. So as you can see here, we did different types of iteration, different types of methodologies of organizing the ribs, different types of boundary of the shell. But basically, you can say for the moment we are concentrating more on the circle boundary. So the main issue that we were facing that is really tricky, that you need to control the profile section, because since you are controlling the, or we can say the vertical section of the geometry, you can control the angles of the cantilevers or within your geometry. So since you are going with the extreme angles, you will face more issues with the buckling issues and more issues also with the failure part. Because as you know, the clay composite doesn't really work with the tension forces. So, and this issue we are trying now to develop in terms of materiality, since we are trying more fibers that will work as a tension system. But still, as I said, we're still in developing this part. But mainly now, I'll try to concentrate more about the design methodology of the geometry for 3D printing process. So we start to test the minimum section, and we found out after different simulations of the overhang angles and trying to know what is the best section line that we can use to print these types of simple geometry. And we started with a catenary arc, and we found out, okay, it was really kind of stable with these types of plate, and also with using a planar system of 3D printing like a Earthen machine. And then, okay, we did something more tricky by cutting the half of the geometry and seeing, okay, what is going to happen like after this. So basically the main issue is that the displacement of the layers and the buckling of the layers, especially if you are not adding more, as I said, more ribs or more small methods that will increase more the stability of the surface, you will face a failure issue through the printing process. So after that, we try to add more, you can say, more, like you can say, like kind of a system of ribs. Okay, we found out, okay, the more you add mass, or the more you increase the surface area by controlling the distances and of these ribs, or also you can say there's a kink within the surface, it will help a lot to print stable layers. So that's what we found out through these small prototypes. So basically what we reach as a find out that, okay, we need a formula. The main formula that will help us, the more you increase the surface area of the shell, it will help you a lot to print kind of printable geometry of the printable, you can say a vault, or you can say a printable dome. So, okay, we found out, okay, this methodology, it will be helpful for us in order to print more complex things with more extreme angles. So we backed to the methodologies that we extracted from Asian masonry building methodologies. And we found out, okay, if we have like a basic methodology and try to mix with other methodology, that probably will help us to print something could cover more surface area. You know, that's what I mean. Like mainly, as you know, there's until now, it's really hard to print a complete roof. Or, you know, so something is not controllable yet 100%. So that's what we are developing kind of in this research. We need to reach something that could be printable and has a specific methodology. Could all the, for example, the buildable or researcher can use it in order to use it, you know. Sorry? In order to use as a methodology in the printing process. So after that, we also we studied like time also back to something the old methods of building with the masonry and how they, for example, trying to carving the mass of the geometry that you are trying to build and trying to stack specific elements inside the whole geometry in order to be stable. So it was a tracking line for us to know, okay, how we can trying to develop a section line that is printable. But for the moment, we tried this only in the small scale, but later we need to try in the larger scale. So basically, these two methodologies, it was extracted from old master building methodologies. Now I'll talk about a third methodology also we are studying. So basically, as I said before, the machinery part also is a part, actually is the main part in order to reach something successful in the printing process. So controlling, you can say, the planes, because basically, since you are trying to print the layers, it's controlled by the points, or we can say the vectors. And now I'm trying to speak in computational design. So basically, since you are doing the contour crafting methods, you are sectioning your geometry. So you need to translate this data as planes and points to your 3-axis machine or 6-axis machine like as a robot. So how we can get benefit from these extra axes? So basically, we found out, other researchers, and we found out that since we are trying to control the layer height and the condensation of the layers, of the earth layers, that also will help us to know how much there is a mass or inertia of this surface of the shell, and how that will be, you can say, how that would be helpful and supportful to print complete shell without any failure. So controlling you can say there's big difference by using non-planar 3D printing process and using a planar process. So what is the difference between two methodologies? The planar process will face more buckling, because you will face like small cantilevers within each layer. But with the non-planar 3D printing, you are preventing these small cantilevers that you are printing. So basically, you are rotating the axis in such a way in order to bond the layer 100% without any small cantilevers. I mean small cantilevers because since you are segmenting, you have like, I can explain it for here. You can see here, for example, since you are printing each layer, it has different angle. So you have small cantilevers within each layer. But if you are rotating these axes to be 100% bonded, you will prevent this issue, and you will solve a lot of buckling issues. So there was a third methodology, but we didn't test it yet because we're still, as I said before, developing extruding system for the robot. But now we are studying the computational and simulation part of this methodology. Also, I will talk about, this is a project developed also at EARC in my master thesis. So basically, it was developing, as I said, a modular system in order to be integrated with the neighbor, a vertical modular system with small cantilevers. So actually, we were concentrating a lot on shells, but we were concentrating on developing a wall with the cantilevers. So like you're mixing vertical element and also you can say the corpels or the cantilever in order to create, kind of circulation way as a methodology. But the main reason that I'm showing this project, that basically we weren't able to build, you can say, we weren't actually concentrating on building a complete roof. Or I think there's other students, we were also studying how you can print a vault or you can say our dome at the ear. But basically now what we are trying to do in our research, we need to merge the two methodologies, a modular system with the shell system. So you have, you can integrate this geometry as a habitat system. It could be integrated with a neighbor. It could be also as urgent shelter. So for that reason, we're trying to find something efficient with less amount of materials and to be printable. So in this video, I can share with you now. So as you can see here, we are controlling not just the amount of layers and the layer height and the way that you control the axis of the machine in order to make a 100% bonding For example, with a robot or with a planar process, you cannot do this, but you can control the path of the layer that you are printing. And also, as you can see here, we are trying to merge two systems, a cantilever with a shell system, in order to integrate different modules with each other by using a wood material, for example. But now I'll show you like a failure. But from this failure, we learned a lot. We learned that in order to print one surface that is supported by itself without any other materials that's supporting the printing process, we need to think about the material type, the way that you extrude the material, and also the way that you control the geometry itself through the printing process. So basically, as you can see here, you can see like it was really a lesson for us, like how you can control the buckling and the failure issues. Basically, this composite, it was only stoneware with sand. So we didn't add fibers and we didn't any helpful issues, but we were controlling only the path in such a way, and we were trying to see, okay, the more you change the angle, the more you will face issues in the printing process. But this is with linearity process. But since you are using a robot or you're changing the axis, the result should be different. And also, we learn lesson like in the printing process, you feel there's a friction issue between each layer. So also this issue, you can solve it by adding more sodium silicate. So it's increase the bonding between the layers and prevent the sticky issue. Because if the material is sticky, you will face friction issues in the printing process. So as a final result, final findings, we were trying to know, okay, controlling the path of the layers, controlling the material composite, controlling the design geometry of the shell system, that we are trying to merge two methodologies in the building process, the surface design, in order to be buildable and printable, and also to be we can say flexible if you want to integrate it with in the construction site or in the neighbor that you want to print your own habitat, for example, or shell. So after that, okay, we found out in order to develop something more advanced, for the moment we're developing like a Python component that will that's the one that I shared with you. It's like, now for the moment it's a simple component. It's just give you like a spiral mode of printing kind of shell geometry, but later we are trying now to develop like slicing methodologies through this component by using Python script in order to understand different types of shell geometries and what is the best way to slice this geometry that help us to simulate, you can say, printable layers or printable geometries. I'm sorry, the screen is not changing now. Sorry.
No, it's working. It's working.
Okay, perfect. Thank you. So after as I said before, like now we are trying to merge the computational tools by using scripting languages in order to understand how we can segment the surface of the shell, how we can add more masses, control these masses in such a way, and if we want to print a complete shell with extreme angles, because we want to cover more area in the plan that we are, trying to cover, you can say. So then after this, as you know, most of the projects that is developed right now with these types of technology, they always add infill design with two surfaces. So basically all projects, all the prototypes that I showed you, it's just using one surface. So one surface. So we are trying to reduce the amount of layer that we need in order to be more efficient, we can say, in the construction side. But this issue, it will show us more problems, as I said, like the failure issues. But in order that we are trying right now in this methodology, okay, how we can develop one surface as an infill design and trying to do a gradient effect in such a way. So this gradient effect will kind of eliminate, or you can say change the layers into, you can say, one surface, and on the other side you have making one bulky rib, we can say, within the shell surface. So it was like a concept that we are trying to also to develop with the other methodologies that we are studying, design methodologies. So as a perspective concept that we want to reach, I hope so, in the final, you can say, in the final goal or aim of this thesis, that we want to reach something in this complexity and to be a printable in the construction side. So for the moment, these things that, like, you can say, still in incremental research. Still a lot of also of my colleague in the lab, Advanced Ceramic Lab in Guimarães, Portugal, and also with the support with different labs, Lab to PT, and this kind of association now in Portugal. They are developing different research projects in terms of ceramic materials, in terms of other materials like concrete and biomaterials. But basically, in my thesis, I'm concentrating, as I said before, on earth-based composite. What the things that we are trying to prevent, how we can solve issues in the printing process, as I said, like shrinkage, cracking, reduce these problems in order to reach like final application we can apply in the construction site. With efficient ways, as I said before. So for the moment, I would like to thank you for listening to me, and if you have any question, please, I'm open to hear your questions. Thank you all. You're welcome. Please, if you have any questions, you can ask me. I think you are developing kind of research in I think most of you, maybe you're developing your master's or your bachelor's. So the main reason also of this workshop that I did with Digital Futures, in order to be more interactive with each other. And if you have any issues, I can simply answer you. Or you can hear me, right? Okay.
Thank you, Fuad, for your presentation.
Yeah,
I think also it's very interesting to see the implementation of the architecture or Islamic geometries and patterns and how we transform it into like to be more able to be printed. So I think there's a lot of research and implementation need to be done on this track, especially.
exactly. Thank you so much, Dina. Thank you so much, Dina, for your response. Actually, I think I've seen your last project, I think, that you did at OTF, right?
Yes, exactly.
It's very,
We did like the one-to-one prototype with the clay printing, and I think it was very good experience that IAC wrote the WASP crane, and we did a lot of material testings, and we faced, as you mentioned, we faced a lot of problems related to the shrinkage and the drying process of the material, especially after the drying. So I think also this opened like um, a lot of doors to have more research in that area.
exactly, Dina. That's what. Actually, I was really impressed by the last prototype that you did. It was really also interesting. So, but as I said, like before, still incremental research. I need a lot to add, if you want to, as I said, to print something, with more cantilevers, as you know, like these issues, it's really hard with this type of research or, printing process.
Yeah, and also one more thing about the timber things. I think we did implement or based our research on the previous projects. I think one of the projects you showed was like related to the relation to the timber with the clay and how we can rest the timber structure on the clay to hold the roof itself. So I think like every year they are developing a lot and exploring a lot of things that they are like growing up to how things is going to be more impressive and more bringing this into reality.
Exactly. Yeah. Thank you so much for your clarification. And please, if you have any also questions, you can simply ask me.
Yeah, I do have a question. Hi, it was
Yes.
an amazing work. I think it was a very good presentation.
Thank you.
So I'm trying to do the same thing, working with soil, which is very local soil in India currently. I'm trying to do 3D printing with that. So somewhere, the first thing which I have struggled with is the material mix. So that, of course, would be different in different countries, in different regions. I completely understand that. So as you were telling about the shrinkage as one of the important things, that is what we were also facing. But what I wanted to understand is, so you were talking about using Python or I think some kind of software for slicing, right? So I've been using just an open source software like Cura. So I wanted to understand how to work upon that and develop it, and how that can help us in in maybe doing better printing.
Yeah. Actually, thank you for your question. It's really interesting. Basically, what we are trying now to develop is computational tool, as I said before, by using Python. The main benefit that we can control the slicing process or the slicing methodology, because it's really critical. Not just about, as you said, the controlling the mix. Also, you need to control the path. If you the path of the material that you are printing, for example, with the robot or with the crane, as you know, on the construction side. So we found out that the computational tools, especially what we are trying to do now, that we want to develop kind of formula that will understand the surface of the geometry that you want to print, and try to understand how you can doing a segmentation of the surface and trying to spread, or we can say manipulate the masses of the surface in such a way to support the whole geometry. So the main reason that we want to develop kind of script that will understand these issues, and that will understand to simulate when the buckling issues or the displacement will happen according to the overhang angles, and also according to the mass amount that you are adding to your geometry or the surface area. So you can say that we are trying to merge different tools, the computational tools, also for sure the material mix, the physical element, and for sure also you can say the fabrication process, because also if you are using a 3-axis machine, so different when you use 6-axis machine, because you're controlling another parameters that will help you to print something more stable. So that was the main. You are welcome. That was the main goal. I've seen like a lot of thanks. Thank you, guys all for. Yes, please.
Yeah, I have a question. Since our research is focused on the recyclability and reusability of clay products, and have there been any insights or any research done in your project into the recyclability, since you're adding binders and also natural fibers, which can be hard to take out of the finished product?
Oh, okay. Thank you for your question. So basically, for the moment, we are not concentrating on this goal, but basically we're trying to add something also kind of recyclable. For example, we studied like there's specific kinds of fibers, or like, you know, as sisal and jute, or like vegetal fibers. So basically also we're thinking that we want to add types of fibers if we mix. So, and if you, for example, destroy the building, so it would be integrated with the environment easily. So, but the main issue now with the binders, as I said, like we use sodium silicate and hexadenametaphosphate. Actually, it doesn't have like a large amount of harming issues in the environment, you know, because at the end they are kind of ions. But honestly, we are not concentrating a lot on the recyclabilities a lot for the moment. We're concentrating more on the problems or issue that you are facing in the printing process. But for sure, like not like if you are printing concrete, you need to concentrate on like the carbon footprint. And a lot of research now, they are trying to mix kind of fibers that reduce the carbon footprint of the materials. But basically now of the composite that we are developing, that we studying different types of common fibers, like, you know, as a sisal, and these kind of fibers, normally it's like environmental fibers, you know, it's take it from the, you know, it's not something chemical, you know, but still, I think maybe that's something, a goal we can tackle in the future. But thank you for your question. Like,
no, one more comment basing off your explanation. Since our research project involves reusing clay stones, not fired bricks, but stones, and they already contain natural fibers such as straw and hay. And this could be maybe an interesting point for you to look into, as using the reconstituted clay stones and the clay and earth from it as a printing substrate or a printing compound, because they already contain these natural fibers and maybe only binders need to be added. So you already have a recycled product to jump off of from.
Oh, okay. That's interesting. Okay, thank you for sharing with me. Actually, I think actually it's really interesting to have something already recyclable and try to print it. Yeah, thank you so much. Any? Sorry.
Do you hear me, please?
No, I'm not hear you very well. Can you please? Your sound is very low.
Now, do you hear me?
Yes, kind of, but not that much.
Okay, I have one question. I just want to ask you, please, about the mechanical model that you have considered for this material. what's mechanical model? And the second question is about the infill pattern. On what basis you choose your infill pattern for the third methodology?
Okay, I'm sorry. I heard that you are trying what is the mechanical model. So, and the second thing, I think I heard that the basis of designing the infill,
Yes.
infill design, right? So basically, the mechanical model, it was based on, as I said, like was based on segmenting the surface in computational way and try to add you can say masses organized in an organized way to support the whole model. But in terms of the infill design base, actually there's something in the design of the infill itself. Like you need to know to make like intersection between the layers, and also we were trying to design to think about the structural performance of the geometry. So we used like a gradient methodology because we need to know, for example, at such a point, at such part of the profile section, you have more surface area and more intersections within the infill design. So you have something more stable. And also at such part that you don't need to support that you don't need to support the surface, so you have less amount of material. So the infill, it will be it has like less intersections. So basically, the two main bases, it was about controlling the surface area at such points of the profile section, and also controlling the intersection between the profile intersection between each cavity of the profile section. I hope that I answered.
Thank you.
You're welcome. And I'm seeing.
I have another question. Do you have any publication that you published the work related to the shell construction and 3D printing, or?
Well, basically, like scientific publication, I have one I will publish soon, like on October this year. But my other publications, it's not really scientific. It's more like, in my master thesis in the, on the EAC platform, or as you know, like it's not really scientific. It's like just sharing the last progress of our prototypes and our projects. But mainly now in my PhD thesis, I'm working on paper with my supervisors that will publish on October. Basically, it's also about additive manufacturing, Earth shell structures, and also in the future, also I will try. I'm trying actually with a colleague of mine from Japan. We are trying also to do a paper about controlling the surface topology of the shell in order to enhance the printing process. So for the moment, I don't have much publications, but there's one that's coming soon, like on October.
Yeah. Okay. Perfect.
Yeah, welcome.
Good luck.
Dina. Thank you so much, Dina. Okay, I think now I finished the hour, but please, I'm open. If you have any extra question, you can send me an email. I think you already know my email, and you can contact me at any time you need me. Okay, thank you all for attending the workshop, and wishing all the luck for you all. Ciao.
Thank you so much. Bye.
Ciao.
Thank you so much.